So welcome to this pre-recording of lecture 27 on three-dimensional plots. So in this lecture we consider plotting of surfaces and space curve. So space curves are here and also our surfaces. They are living in three dimensions. We can also use three-dimensional plots to get an idea on how complex curves look. And we will end this lecture with an example of a four-dimensional plot, which represents the Riemann surface of a curve. Okay, so let's make the most important distinction is between surfaces, which are two-dimensional, living in three space, and the space curves, which are one-dimensional. A surface can be defined explicitly, the height in function of the other two coordinates, x and y. Another way to represent surfaces is via one equation in three unknowns. For this we are using the implicit plots. So the other representation is by three functions in two variables which define the coordinates of the surface. So why two variables? Because the surface is two-dimensional in three space. So for space curves, we can define a space curve also by three functions, now in one variable, because a space curve is one-dimensional, or we can define a space curve by two implicit equations, so as the intersection of two surfaces. Okay, so there's lots more interesting things going on than in two dimensions. So as always in this course, I will start with some slides about the plots that we are going to make. So here is the first plot. It's a symmetric plot. We consider the cosine of x and y, and we can color this. So this looks like a heat map. The redder the color, the higher for the highest points. We see also the symmetry and the periodic nature of this surface. So this is a static picture. When we go to the Jupyter notebook, we will be able to rotate and to adjust the viewpoint. Here is a surface defined by one equation in three variables. So this is done, the plot is then made via an implicit plot. One of these issues is here that at the origin, one cannot see it that good, but the origin is kind of a special point here. So this representation is definitely not the best representation. From calculus, you might have seen the concept of surfaces of a revolution. It's actually a perfectly nice symmetric surface. So if you see the profile, you know how the height is defined in one of the coordinates, and then you rotate that profile along the vertical axis. So we will also be able to explore this aspect of the surface when we can rotate the viewpoint. Okay, as functions, either explicit or implicit. Here is another special surface defined by two parameters. So we have three functions, one for each coordinate, x, y, and z, and we have two variables, u and v. And I will show the recipe how to draw this heart-shaped surface. So, space curves then. So here is a very well-known and well-studied type of curve. It's what is called the twisted cubic. So given in parameter form by three functions. The curve is given here, of course, with a certain thickness, otherwise one might not be able to see this. And one has quite a nice recipe. So this t runs from -1 to 1. Then the x runs from also -1 to 1. The y goes from 0 to 1. And the z, the height, takes this shape of a cubic. So it's a twisted cubic, so it's a cubic curve when one looks at the height, but if one looks to the relationship between x and y, one has a quadratic relationship. So this cubic is twisted because it moves along a parabolic cylinder, and that can be made explicit via the plot using the two surfaces. The intersection of these two surfaces defines the space curve. So what you can see here is the blue. In blue, so drawn in blue, we have the parabolic cylinder. So y equals x squared. So in the plane, this is a very simple parabola, but here the z can be anything. So you consider all lines over y equals x squared. So that's the blue cylinder. In green, we see the cubic surface defined by z equals x to the power 3. So that's also what they call surface that is ruled, where you have the y-axis that essentially moves over the surface, over the cubic curve in the xz plane. Again, by changing the viewpoint, and that's the motivation to go to the Jupyter notebook with the SageMath kernel. Changing the viewpoint, one can zoom in, or one can look at the parabolic nature of this curve, or at the cubic nature of this curve. So these are three-dimensional plots. Can we go beyond dimension 3? Actually not, but we can try. So here is a four-dimensional plot. I will try to explain. So what we are trying to plot is the cube root. So we have the surface z equals w to the power 3. The input is the w. So we have two input parameters, the real and the imaginary part of the w. So this will be the x and the coordinates that come from the input. The height is the height of the real part, so the height of the surface is the real part of the cube root of this number. So as we have seen in the course, the square root is a two-valued function. The cube root has three values. So if we pick one value for u and v, imagine a line starting here somewhere in the plane, then we have the line hitting this surface at 3 different places. There's one very specific place, and that's when u and v are both 0 when we are at the origin. This is when we have a singularity there. Now, why is this a 4-dimensional plot? Well, the colors represent the imaginary parts of the cube roots. So one could imagine, one could think that the surface intersects itself. So we have the red, and then we have the yellowish orange. Here you see at this intersection where we have the same real part, then the imaginary parts are distinct. And we see this as the colors are different. We are going to try to make this 4-dimensional plot. So let me shift the slides away and go over to the Jupyter notebook which I prepared. So we start out with surfaces. So I'm going to make a new Jupyter notebook. So in this notebook we make, so this is lecture 27 of the course Introduction to Symbolic Computation, running in the 8-week summer session. So when we are making 3-dimensional plots, we think of surfaces or we think of curves. So it is very important to make that distinction because the commands are entirely different. So let me start out with a markdown cell and another markdown cell, which for the first part on surfaces. So the first type of surface is given explicitly by one equation. So explicitly we express the height of the surface so the height is z as a function of the x and y. So what do we have? We have that z equals f of. Okay, so our first example is to plot the cosine x times, let me make it explicit, z with a dot, for x in the interval minus pi plus pi, and also y in that interval. So we saw in 2 dimensions we were using the plot command. Here we will be using the plot 3D command. So by default plot is 2-dimensional. I have to define, so I'm going too fast now, I have to define my expression first. So it's an expression in 2 variables, x and y, and I will define my expression as x times, as the cosine of x times y. So one source for difficulties is that you haven't defined your expression correctly. So it's good to do that in a separate coding cell. So then we have the plot 3D of f, where I have to give the ranges for the 2 variables in the expression. So that's minus pi pi. So surface is two-dimensional, and in this explicit representation, we can choose the x and y independently from each other. So here is then our first plot. So the first thing that you notice is that it's rather flat. The other thing is that if you are clicking on this, you can start to rotate. So you can get a feeling, so you can move it up or down or left or right. In the next lecture, we will see animations, and a spin plot is a very natural animation on these surfaces. Now, we also notice that it's rather flat. That's because the minus pi to pi is much larger than the horizontal than the vertical. So I can make it less flat by changing the aspect ratio. So let me do this. So I can say that the scale for the z, for the third coordinate, should be twice that of the scale for the x and the y. So now you see that this comes a little bit more like a cube. Perhaps if I really wanted a cube, I could take 6 times or 4 times. So let me now try 4. So then you can see that this looks way more like a cube. But perhaps 4 was too much. Perhaps the best value was actually pi. Okay, so the picture looks rather monochrome, monocolored. So let me add some colors to it. So I can specify what I don't really care on the type of color, so I will use the parameter automatic, and the automatic is still not very good, so I have to specify better the number of colors. So let me use 256, which is a nice number. And the coloring is still not what I had hoped. There is one more parameter that I can try. So I can set the adaptive to true. And now I have my picture. So this is a nicer picture that gives the color coding relative to the height. So the you can see that a surface is approximated by patches, and I can change the number of plot points. I can specify to use more plot points. So let me try to do this. So the plot points, I can specify this in both x and y. It might be that 100 is still not good enough, so let me try 500. And the patches should actually get smaller. Okay, so these were the explicit plots. We can change the aspect ratio and apply a coloring. So let me make an implicit plot now. So in an implicit plot, I have also three variables. So now I have to declare three variables, but let me say what we want to plot. Plot the surface defined by the equation z to the power 3 minus x squared minus y squared. So defined by an equation for x and y. So x and y are positive. For x, well, they are squares, I'm sorry. For x in the interval -1, 1, also for y in the interval -1, 1, and for z in the interval 0, 1. So we take the well, we can try to define what the surface should look like. So we kind of take the height. You can still isolate z to the power 3 at the left of this equation, and then x squared plus y squared to the right. It's kind of that we take a cube root of a point, and the farther away from the origin, the larger the cube root will be. So now I'm using implicit plot 3D, and again I'm too fast, so I get this error already. So now I have to declare also my z variable. So I will redeclare x and y as well, just to make this part of the plot self-contained. So I define my equation, I assign it to f, and it's good to isolate this, so I'm sure then that this looks good. I didn't make any typos when I defined the equation, so I will now do implicit plot 3D of f and specify the ranges for x, for y, and for z. So notice the difference with the plot 3. And here you see the plot. It's kind of a cone. We can turn this around, and you can kind of see that it should touch the origin, the plane, but in some sense the cone gets too narrow. So this is not really a good plot yet. So one can improve this by choosing more plot points. And the exercise, so we went to polar coordinates last time. We can choose polar coordinates for the x and the y and make them a polar plot. So that will be a better representation for plotting surfaces like this. So you see it's actually a surface of a revolution. It's very nicely symmetric. So that's another indication that you can plot this much more efficiently than with the implicit plot 3D. Okay, so one last surface is the heart-shaped surface that are shown. So let me, I will copy and paste this from the prepared notebook. So surfaces can be defined by three functions in two variables. So why two variables? Because the surface is two-dimensional and we need three functions, one for each coordinate. So here you see the definition of the three functions, so I can print them. F of x to also double check f of y, and then printing the f of z. Okay, so now I will have to use the parametric plot 3D, where I provide a list with the three expressions. So I called the expressions f of x, f of y, f of z. And I have to provide a range of the parameters. So you can see that the u is given as input parameter for a sine function. So the natural range is minus pi to pi. For the v range, I will pick 0 to 1. Okay, so this takes a while, and it's actually not really that good. So what's the problem here? Well, my range was actually not very good, so it should have been -1 for v. And also, since this will turn out to be a heart-shaped surface, let me put the color in red. So the range is from -1 to 1. And now you still see that there is something wrong. Or, well, no, nothing is wrong. So I had to rotate this in the proper way. So here you see the heart shape. So how can we rotate this? So here are the tools on how to do this. So one can provide the rotation. So I'm copying and pasting this here. So one can provide the angles, and in my case this is still a little bit hit or miss. So you experiment till you find the right angles, and then I'm going to show the picture without frame and with a smaller figure size here. And in a way this still doesn't look the way I had imagined it, but you can still adjust this. So this is a curve. You can see the recipe here. Two variables, so two parameters, u and v, and three defined by three coordinate functions. So we rotated the axis, so the surface was entirely not in the orientation that we wanted to see. So the x and y axis were rotated, also the z axis with this angle pi/4. In the next lecture we will see animations, and one can make this more automatic. One can do the rotations in an animation for a whole wide range of angles, and then get a better idea of how the three-dimensional objects looks like. Because I forgot to say that actually when we look at a screen, we still look at a two-dimensional representation. Okay, so enough about surfaces. We are halfway in. So let's look at space curves now. So this is my second section. And we look at the twisted cubic. So the twisted cubic is defined in parameter form by three functions. So I will write them very explicitly. So we have the parameter t, which agrees with the x coordinate. So I could use essentially x as parameter. So three coordinates, three functions. So let me then define my variable t, and my three expressions are, so I can do this with a tuple assignment. I call my functions not x, y, z, which is a little bit too common, but I call them xt, yt, and zt. So this is my tuple assignment. Okay, so what function are we using? Well, we have used it already. It's the parameter plot 3t. So now we provide the tuple. So I will assign this parametric plot 3d. And essentially what I could have done is, and what I perhaps should have done, is I could have assigned this to something, so twisted. Then I do not need to retype, which will lead to the introduction of errors. So I have my tuple with my coordinate functions. Then I have the range for t, from t going from 0 to 1. Now I need to choose a thickness. Let me take thickness, and 10, and a color. Let me pick red. So I've assigned this to the plot of the twisted cubic pt. What has been computed is the plot, and this has been assigned to the variable name pt, and I can now show this, render it with the show command. So here it is, and the viewpoint again is rather not really that beneficial, but here you see the twisted cubic. So if one looks at it, so you can see the parabola coming up, and you can also see that it looks very much like a cubic. So the origin is an inflection point, so the concavity changes. So we can see this, so we can see the parabolic cylinder. So let me start with the parabolic cylinder first. So the twisted cubic is defined, lies on a parabolic cylinder. And the parabolic cylinder can be gotten from the parametric equation. So the twisted cubic, the coordinates satisfy an equation. So the parabolic cylinder defined by x to the power 2 minus y equals 0. So I'm going to plot now two surfaces, and I've saved the twisted cubic in pt, so I can combine the two plots. So I have the implicit plot 3d of the surface defined by this equation. So I don't need to give the equation, but I must provide the range for x, the range for y, and the range for z. So actually the range for y is between 0 and 1. The range for z goes from -1 to 1. So this defines the surface, and now I can plot the twisted cubic and the parabolic cylinder all in one figure window. And here it is. So the viewpoint is actually quite nice. You can see the parabolic cylinder, and you see that if I start twisting this, so we see the twisted cubic that kind of goes from one end point of this parabolic cylinder to the other parabolic cylinder. And the thickness is thick enough so you see it sticking out on both sides. So again, the advantage of you can tumble this around and see this in any point of view. So this is one surface. So this is the surface that makes that this is can be seen as a quadratic in x and y. The other surface is defined by the equation x to the power 3 minus z. And now I'm going to give the same ranges. So these are tuples. If I wanted to be a little bit more economical, I could have assigned these tuples into variables as well. So here I have the other cylinder, and now I can make the combined plot of the twisted cubic, and I should have given another color, so let me make the color green. And now the default angle or the default orientation is actually also quite favorable. So you see the green surface, and if I rotate this, you can see that indeed the red curve lies on this green surface, and you can see that it traces this out from one end to the other end. So here you see the twisted cubic, and I invite you to look at the Jupyter notebook. Either make it yourself, which is strongly recommended, or to look or to download the notebook posted at the course website. Okay, I have 10 minutes left to demonstrate how we can go beyond three-dimensional, how we can make a plot of a Riemann surface. So that's the last section, looking at four-dimensional plots. So the example is to plot. So we want to look at the cubic root defined by z equals w to the power 3 for w equals u plus I times v. So I have four variables. I have the u and the v for the input, and I have the x and the y, which are the real and the imaginary parts of the z. So let me define u and v first as real variables. So that means they are belonging to the domain RR. And I define w as u plus I times v. So I can check the real part of w will be u, and the imaginary part will be v. So let me now define the other two variables. I have the third power. X will be the real part of z. And here we have the benefit of working with, so there is still something wrong here with this y. I most likely must, I'm now a little bit curious why the y comes up. Okay, so I better reset, because the v was still defined from my heart-shaped surface. Why this shows up is still kind of a mystery. Let me continue. So it's a mystery to me why am I seeing the y? Well, I need to. I thought I had. Oh, because I made a typo here. Okay. Everything is all right, except that it's at the end of this recording. So we have now the four variables defined. Now, before I do the plotting, I will transition to polar coordinates. So I have rectangular coordinates, but I will, for the input, I will use the coordinates I will replace in x and y. I will replace them with the polar coordinates. So let me continue here. So I have my representations for the output in x and y. In polar form, they will be given by these expressions here. So I have px and py. So I will plot them now in a parametric plot. So I have the coordinates for x and the coordinates for y, and the height is the input parameter r times cosine. So let me do this and then try to explain. So the x and the y coordinates, and this comes from the square root, and I will plot this as a tuple now, as a list, I'm sorry, for r in the range from 0 to 1 and t ranging from 0 to 2 times pi. And here you see that I have the shape of my cube root. So the height is part of the um, value that gives me. So I'm plotting the cube root for the input, the W, U, and the V. So the output is the height given by its parametric form. Okay, so now the last color coding. So I will define a color map that gives me these red and yellow orange definition. So the imaginary part is defined by r times the sine function. So this color function will, for every value of the radius and the angle, it will return a value. And for that I will be using the color map that is abbreviated here. Okay, so then my last plot, which as you can see, I do not type in, but copy and paste from my prepared notes. So you see, using the color map, I get to see the representation of the cube root, where the height is the real part and the colors are the imaginary part. So the default view is actually still quite good, so let me try to spin around to give an impression on how the surface goes. So it is a little bit like a parking garage. So if you climb on one sheet, or if you start on top here, you circle around, and then at some point you will come back. So you will loop. You don't really intersect. So it looks here as there is an intersection of these two surfaces, but since the color coding is different, we have different imaginary parts. Okay, so I'm about at the end of the 50 minutes recording. I hope that this lecture was not too confusing. Notice that 50 minutes is actually too little to show every capability of the scientific and symbolic computing part. What is important is that you realize the difference between the two-dimensional surfaces and the one-dimensional curves, and the implicit forms and the explicit forms, and the parametric forms, where here in the last example I went back to the polar representation. So the next lecture will deal with animations, both in 2 dimensions and 3 dimensions.